Morning, everybody. How are we doing?
Good, how are you?
Yeah? We looking forward to spring break?
Yes.
Yeah? All right. So we left off last time with what we call Thompson's flying ring, right? The rail gun, right? Where I shot the little things up. Okay? So we're going to continue that idea, right? Of like motional EMF and applications of Faraday's law and Lenz's law. And before I can do any more applications, we need to talk about the elephant in the room, okay? Because we've kind of hit it the whole time, but it's there, right? So let me just write down Faraday's law of electromagnetic induction, okay? I'm doing it here. Okay, fine. Right? What's this? EMF. But what is that? It's a voltage, right? Like it's a fancy way of saying voltage. There's this weird idea that EMF and voltage are not the same thing depending on the circuit, but for this class, EMF and voltage are the same thing. It's okay. But this is voltage, right? And what shape is it? I know that's a weird and funny question because voltage is a scalar, is it not? Right? So when I ask what shape is that voltage, your brain should kind of go, oh, what? But you did it yesterday. We've been doing it for a lot. What shape is this EMF? It's a circle. It's a rotation, right? Because we induce these EMFs in loops, don't we? Now the loops can be rectangular, it's true, right? But really what we've got here is a voltage that is circulating. And voltage doesn't have a direction. Strictly speaking, voltage, golly. Try again, Mr. Balogh. Voltage, current, and resistance have a relationship. What's that right that I just wrote down? That's Ohm's law, right? Instead of a V, I wrote EMF, but it's Ohm's law. And of the three things in Ohm's law, one of these does have a direction. What is it? It's the current, right? So in physics, we tend to sort of play fast and loose with this connection between EMF and current. And you've already heard it a lot from me without maybe realizing it. Or maybe it just confused you and continues to confuse you. But sometimes I'll say the current induced in a coil from Faraday's law of electromagnetic induction. You're like, what current? The current is there if resistance is there, right? The EMF is always there. But if there's resistance in the coil, and there always is in a metal, right, you're going to have a current going along with it. But if we back up even further, there's another relationship to a field that involves voltage. What field am I talking about? Electric field. An electric field is definitely something that has direction, right? So if this, so here's a coil of wire, right? And if we've got like a magnetic field that's changing, right? And that magnetic field is increasing, right? Lenz's law will give us a direction that the coil will produce a current in order to fight the change in flux through it. So if the flux is increasing pointed into the screen, what does Lenz's law have to say about that? An increase into means I'm going to increase out. So I hold my thumb out, my fingers wrap around in the counterclockwise direction, and I have this current, right, that's induced, that's inducted. Same difference. Induced, there we go, okay. And so what does that mean for the voltage? Like as we go around this loop, what direction is the voltage? Like where's the high? Where's the low? It's kind of around, right? If the current's flowing around, then the voltage is taking us in that same direction, right? So if the current's there and there's a voltage that kind of goes around this thing, what's the electric field in the wire doing? Also going in a circle. The electric field in this loop is a circle. What does this electric field look like? I know it's a circle. What other field makes circles? Magnetic fields. Right? Magnetic fields are closed loops, are they not? But in Faraday's law of electromagnetic induction, we not only generate a EMF, a voltage. We not only generate a current, those things exist because there is an electric field that's causing them, and that electric field is a circulating electric field. This is the same electric field, but it doesn't start on a positive and end on a negative, the way we've always counted on our electric fields doing. This electric field is a continuous circle. So, that being the case, I can write the path integral of that electric field in its pattern, whatever path it takes, as long as it closes on itself. I can write that. That is equal to a voltage. It's a definition of voltage. You want to go back and look at that chapter. And that is going to be equal to the rate of change of the magnetic flux. What's in green is a new kind of electric field. It's an electric field that is caused by a changing magnetic flux, probably a changing magnetic field, right? But this field circulates. So what does that mean? That means we now have 4 equations for everything you have learned about electricity and magnetism so far. Ooh, they're called Maxwell's equations. We won't talk about why until later, but here they are. You know this one. What's that one? That's Gauss's law, right? Gauss's law, which is a summary of many things. It's got Coulomb's law in it. It has electric field in it. It has the idea that the fact that the flux is equal to a constant, like the charge enclosed by epsilon naught, that says that electric fields have a start and a stop, that they start on some kind of charge and on another kind of charge. The flux isn't going to be 0 because there's a source somewhere, a beginning and an ending to that electric field. And then we write down, for completeness, we write down Gauss's law for magnetism, which is equal to what? It's 0. Why is this 0? Because magnetic fields form closed loops. And any flux heading out of a closed surface to a magnetic field line heading out, it doesn't terminate somewhere, right? There's no charge anywhere for it to terminate on. There's no magnetic charge. And so it just comes around, comes back in through the closed surface, and you're always, always, always going to have 0 as the answer for the amount of magnetic flux through a closed surface. It's not a useful equation in terms of like doing math or solving anything, but it's vitally important as a pillar of electricity and magnetism. These two equations on the screen are telling us that these two fields are different, that the electric field is uniquely separate from the magnetic field. Electric fields start and stop on charges, but magnetic fields, they form closed loops. They're dipolar fields all the time. So again, very important statement, even if it's not useful the way that Gauss's law is useful for finding things. However, introduced in last chapter, there was a law that acted like Gauss's law a little bit, but it was for like finding magnetic fields of things kind of quickly. Do you remember what it was called? It's not Faraday's. It's Ampere's law, right? And what Ampere's law said was, look, we're going to form a loop, right? That integral right there says integrate the dot product of the magnetic field around a closed loop, that ds, right, with the circle on the integral. And we found that to be equal to a different constant. But again, sort of this same idea as Gauss's law in the sense that all we need to know is the amount of current enclosed. In other words, where do magnetic fields come from according to Ampere's law? They come from currents. And if we want to dive a little bit deeper into that real quick, in order for a current to be in a wire, what must also be in that wire? Voltage and we just talked about it 5 minutes ago. Electric field, right? If a current's there, a voltage is there, it means there's an electric field there, right? But interestingly, this electric field that's hiding inside of this current is a steady state electric field, right? It's not an electric field that's changing and getting bigger or smaller. It can, that just changes the strength of the magnetic field. But this is the first, Ampere's law is the first time where we see that electric fields and magnetic fields are coupled together. That a steady state electric field along a wire will generate these circulating magnetic fields. And then along comes Faraday's law. And what does Faraday's law tell us? If a circulating magnetic field in Ampere's law, if a circulating magnetic field is caused by a steady electric field, then a circulating electric field is caused by a what? Not a steady magnetic field, but a changing one. And you're like, ugh! Like the symmetry kind of broke there, didn't it? A circulating magnetic field in Ampere's law is caused by a steady electric field in that current. But a circulating electric field needs a what? Changing magnetic field in order to circulate. So there's a tiny bit of a yin and yang there, right? An electric field can cause a magnetic field to happen. Can a magnetic field cause an electric field to happen? Yes, but the magnetic field needs to do what? It needs to change, right? So it's not quite symmetrical. But one of the things that Maxwell's equations does is it outlines the fact that the electric field and the magnetic field are distinct from each other. But it also says that they're connected. That electric fields can create magnetic fields, and that changing magnetic fields can create electric fields. So we're starting to see some symmetry there. It's just not a real great symmetry. But these four equations summarize everything that you have learned this semester so far. That's your whole note card. This is your whole cheat sheet, okay? Right? Maxwell's equations are that thing. Now, notice that each one of the subparts is named after somebody, right? Gauss, Ampere, Faraday. But the collection are named Maxwell's equations. So naturally, you should be asking the question, what did Maxwell do, right? That was so amazing. Obviously, he didn't just put all four together and say, I'm done, okay? Spoiler alert, one of these is wrong. Wrong might be a strong word. It's incomplete. And we're not going to find out why it's incomplete until after AC circuits. Okay? So we'll get there, we'll get there, we'll get there. But the hint lies in the current writing that I've got on the screen for Maxwell's equations. There is an asymmetry in these equations, and Maxwell is going to fix it. Okay. In the green box, you'll notice I've kind of been writing this very particularly, right, with its minus sign and its integral. That's what I call the real Faraday's law. The Faraday's law we use, the voltage equals the change in magnetic flux with either a minus sign in the front or the absolute value signs. That's like the practical version, right? But the thing in the green box, the thing that I put in Maxwell's equations, that's the one, right, that tells us all of the information we need to know about what electric fields look like in Faraday's law of electromagnetic induction. So I want to play a little video clip for you right now to try to help you see what's going on here from my famous old video clip collection that don't get copyright struck on YouTube. And then we're going to move on, and I'm going to show you some demonstrations about how to apply like everything you've learned in physics so far.
But when the magnetic flux through a loop changes with time, it creates an electromotive force around the loop. And that electromotive force is due to an electric field whose line integral is not equal to zero. In other words, there is a way to make electric fields circulate after all, and it's accomplished by changing the magnetic flux.
Change the flux.
When
right?
Faraday discovered that a changing magnetic flux could make an electric field circulate, he added something extraordinary to the laws of electricity and magnetism.
Do you see? So they were drawing the tangent lines, but that's a circulation pattern, right? So you go around a circle at every point, you've got a tangent line. So that flux going up and down, right? No, I know. You can go either get the recording or this comes from a series called The Mechanical Universe. And they're freely available on YouTube, posted by Caltech, that have the full episode with these animations and all the context in them. All right, so let's talk about eddy. So, what's an eddy? What's an eddy? Yeah, okay, so water. So flowing like a river, like a river's flowing water through. And if you see an eddy in the river, what is that?
Eddy is moving water.
Yeah, but like specifically, what is the moving water doing?
Flowing.
It's a circulation. So a whirlpool is an extreme eddy, okay? But an eddy is a circulation of something, a small circulation. So as the river flows, you might get an eddy forming where there's a portion of the river that's kind of swirling around maybe a log or a rock that's in the bottom, right? They tend to be temporary things, right? The eddy will break up and the water will continue down. Eddies occur in air, circulation currents in air, and eddies occur in metals. Because what shape is this induced electric field and current when Faraday's law is involved? It's a circulation, isn't it? So an eddy current, right, is a circulating current that is produced in a conductor when it experiences a change in magnetic flux. And I'm going to do a little bit of a shorthand here. I'm going to say a changing magnetic field, okay? Because flux can be magnetic field area or the orientation, right? But we're just going to talk about changing magnetic fields for now. So, what is this? Spatula? Okay. What is this? This is not a spatula. Lewis, I got you, bro. This one's for the cats. Yeah. Okay. Go ahead. No, don't do that. So hair comb, right? Okay. Spatula, you use that term correctly. This is not a spatula. Does anybody know technically what this is in the kitchen? A pancake turner. Or a turner. Sometimes they're just shorthanded as a turner. A turner has slots in it. This is a spatula. It's a turner. I know of what I speak. Professional chef, if you walk up with a good spatula and you hand him this, you're going to get clocked. Okay? This, notice the difference between a spatula and a turner. This one's solid, right? There's no holes in it. This is a turner. But everybody calls them spatulas anyway. Okay. But I educated you on the finer points of cooking. What's that? SpongeBob is using a pancake turner, yes. Destroying everybody's childhood one step at a time. All right. Am I allowed to admit that I really don't know SpongeBob at all? Yeah, my kids were a little bit too young for SpongeBob. They never really got into it. My kids were really into Phineas and Ferb. And so we watched a lot of Phineas and Ferb. Phineas and Ferb, My Little Pony, the newer version. Yeah. Avatar, Last Airbender. Yeah, we did a lot of that. Okay, so what have I done here? I've oriented it wrong. I've oriented it in a way that you guys are not going to be able to see it very well. So let me, is my thing too narrow? Oh, this is going to be close. Okay. All right. Do you see how I have set up my system here, right? Okay, I've got it so that the spatula passes through my variable gap magnet, just like you guys had yesterday with your coils going through, right? Okay. Now, without this magnet here, it's a pendulum, right? And my pendulum's going to die fairly quickly. I can hear the squeaking. Okay, so there's friction in there, right? But it's still going, right? Okay. So if I take my conductor here, my spatula conductor, right? And I lift it up and I let go. What's going to happen? So it's going to come in. Is it going to experience a changing magnetic field? Yes. Okay. So that changing magnetic field is going to cause what to happen? It's going to cause a circulation, right, in the metal of the spatula. In other words, there's going to be an eddy current in here. There's going to be a current that's going around in a circle, right? What do we know about that current? Think Lenz's law. It's opposing what? It's a current that is made to fight the change in magnetic flux through this conductor, right? So it's going to fight on the way in, right? And it's going to fight on the way out. How much is it going to fight? You ready? Do you in the back want to see it again? You can stand up. It's all right. I know it's down low. What is this?
Levitation device.
Not levitation. It's what? This is a magnetic brake. What's a brake? Something that stops something, right? How do brakes and normal brakes in cars work? Friction, right? There are these pads. When you push the pedal, a hydraulic system squeezes the pads onto a center disc that's attached to your axle and tire wheel, okay? And as those pads come down and squeeze on the central disc, this is my head, right? Okay? Those pads come in and squeeze, it causes friction in that disc, and the disc heats up and all that kind of stuff, right? What is a magnetic brake?
Magnetic friction.
Exactly how much friction do I have in this system? Pretty much zero, right? However, we were able to make it stop without having it touch anything. What are the advantages of magnetic brakes?
They don't require touch.
No friction, no pads to ablate, no pads that need to be replaced.
Cheaper, more money.
Not cheaper. Okay? But it goes better. So in this system I have right here, where is the energy going? Energy has to be going somewhere. Well, okay, the magnet, it's not supposed to move. So where does the energy go?
Into the magnet.
Into the same place it went yesterday in your lab. Into the resistance. The resistance turns the current into heat. Okay? So we're generating heat here, just like we generate heat in regular brakes, right? And heat is lost energy. Heat is not, you can't really so in your car, you're driving along, running on gas, running on old dinosaurs or whatever, right? And you hit the brakes. So you just converted a lot of old dinosaur chemical energy. I know it's not dinosaurs, it's old plants. You converted a lot of chemical energy into mechanical energy, and now you've converted all that mechanical energy into what? Thermal energy, which you cannot store in your car. If instead of letting this go into heat, I capture that current, that voltage, and I attach it to a battery, what are we doing now? We're charging batteries with the mechanical energy. This is how electric cars extend their range. You use electrical energy to turn it into mechanical energy, but as the car slows down, if you're not using the actual brakes, you just let the car slow down with its regenerative brakes, it stores that energy back into the battery. It's not 100%, because there's air friction, there's the heating that does occur inside of the regenerative braking system. So it's not a 100% capture of the energy, but it's better than zero that a conventional car would use. So eddy currents, there's a current that's being generated in here that circulates. That circulating current is fighting the change. It fights the change on the way in and on the way out. Like it tries to push it out when it's coming in, and when it's in and trying to leave, it pulls it back inside. Okay? So let's compare and contrast that with my pancake turner, right? Now, what's the kind of the big difference between the spatula and the pancake turner? There's some holes in here, right? So what does that mean about the eddy currents that can form in the pancake turner? They're smaller, right? They're like physically constrained inside of this shape. So if I let that one go through, now did it stop? Eventually, like it did like kind of almost 2 swing throughs before it stopped, right? Whereas this one 1, 1.5, something like that, okay? Now let's compare and contrast that with the hair comb. Pitchfork, whatever this is. Now, eventually it did stop, right? Okay? So why is it that the pitchfork seems to not have very many, but the pancake turner does seem to have almost as much as the spatula? There is one big loop around the pancake turner, right? Because it closes off this side. So there's a big eddy current that can be there, right? But here there's just a lot of little tiny eddy currents and they never really get a chance to do much, okay? So what's the advantage though of, say, the pancake turner versus the spatula from like an engineering design point of view? It's less material, it's lighter weight, right? And you can get almost the same amount of braking, right, with a lighter structure. So, magnetic braking brought to you by Faraday's law of electromagnetic induction. Regenerative braking brought to you by Faraday's law of electromagnetic induction. Electric cars brought to you by Faraday's law of electromagnetic induction. All right. Let's see. There's 2 chances for me to die today. This is the first one. This may not lead to death. This would lead to grievous personal injury. The other one would definitely lead to death. Okay. You guys, do you have any? Yeah, okay. I need you, Tyler, would you verify something for me? Okay. Put that on the piece of metal that's down here underneath your desk.
Top it?
It just doesn't matter. Sideways. Okay. Is it a magnet?
Yes.
Yes. Okay, pull it off. Okay, do the same thing with this one. Is that a magnet? Okay, so give me the not a magnet. You've got the magnet in your hand? Okay, so Tyler has verified that he has the not a magnet in his hand, okay? I'm gonna let him hold on to it because I don't want to do a switcheroo, right? This is the not magnet part. What is this? It's a pole, but more importantly, hollow pole. Is there anything in it? Yes, there is something in here. Air, good job, okay? Always see what's there, not what you expect to see. Okay, here comes the grievous personal injury part. Okay, I'm going to take this not magnet, which is the same Tyler, they were about the same mass, weren't they? I didn't ask you about that, but they are the same mass, okay? And I'm going to drop it into this pole. Julie, can you lean over and catch? Are you uncomfortable? You good? Okay, here we go. 3, 2, 1, go. Okay, so how long did that take? About a set. Let's do it one more time, okay? 3, 2, 1, go. Okay, you okay? It's not hurting you?
No, I'm good.
Okay, all right. Okay. Ooh. My knees don't like that. Okay, you take that. So do you have the not a magnet now? Mm-hmm. Check, just make sure. Yep. That's the not a magnet. So I have the magnet. I don't want anybody to accuse me of cheating or magic or sleight of hand or anything like that, okay? All right, just give me a second, Julie. All right, so now I'm going to take this magnet in this aluminum pole. This magnet does not want to stick to this aluminum pole. Aluminum is just not magnetic at all, right? But it is a magnet, right? Okay. You ready, Julie? 3, 2, 1, go.
Oh, I see. It was going slow. Anyone counting?
Ah!
That took 10 seconds. I counted. Yeah, someone was counting.
What's in the pole? Air. Good. Okay, right? So this took a lot longer to get down the pole. Why? Faraday? Yeah. Okay, good. We know we got to blame Faraday here. It's so agonizing, isn't it? We can teach a whole lecture while it's taking us time to get down it. Okay, so I dropped the magnet into the tube. This tube is what? Aluminum, which is a conductor, is it not? It's basically a big, long coil, isn't it? It's like a bunch of conducting loops stacked on top of itself. So this magnet comes inside to where the coil is, and the coil, seeing a changing magnetic field, says what? No, right? Lenz's law, just meh, right? So magnetic field goes from 0 to something, Coil goes, creates a magnetic flux to oppose the change in magnetic flux it's experiencing, which causes this magnet, which was falling, to do what? Come to a stop. Slow down and come to a stop. Okay, the magnet has now stopped. What's the change in flux? It's now 0, right? Because the magnet isn't moving. And so the coil goes, so what? There's no changing magnetic flux. Is there field? Yeah, but is the field changing? No, the flux isn't changing. And so the coil goes, I don't care. So it stops making a counter flux, right? And so what does the magnet start to do? Starts to fall. As soon as the magnet starts to fall, there's now a changing magnetic flux. And so the coil says, nah, and causes a flux opposite to the magnet, so the magnet comes to a stop. Now that the magnet is stopped, what does the coil do? Whatever. No current, no counterflux, so magnet begins to fall. How many times do I have to repeat this? As many times as it takes, right, to get to the bottom. So the question then becomes, why doesn't it just get stuck? Why isn't it just hovering inside of the pipe?
We got gravity.
No.
What also
What's that?
It falls a little bit at a time
Why?
because of the changing flux.
But the changing flux should like perfectly just let it hang there. But why isn't it as soon as it tries to start to move that counterflux isn't just forcing it to not move? Well, resistance. Yeah, it's the resistance of the pipe. What happens if this were a superconductor? It would just float. And I already showed you, right? I showed you the superconductor when I had the liquid nitrogen, right? And that magnet just floated, right? Then I have to change the magnetic field through this coil to get it to launch.
So instead of changing the field around the object, you change the field around
Inside the coil and let the coil move. Yeah. Okay. All right. Let's see if I die. Oh, no death. Okay.
Sorry. I was trying to steal it.
Guys are back on railguns again. All right.
falling.
Find the vector of my hand as I'm falling.
Okay. Where was I? Ready? Okay. Where did my... Oh, it turned off. Let me get this running again. But I'm pretty sure that now that I've taught you about eddy currents and I've showed you Maxwell's equations in their admittedly preliminary form, okay, we can now do this. The entire semester has been building to this because what I'm about to show you, okay, what I'm about to demonstrate, okay, is everything that you have learned about electricity and magnetism in one machine that's labeled with very scary stickers, okay? So I want to start getting this set up, okay? And while I'm getting this set up, sort of getting the setup started, I am going to play a video, okay? This video is going to, I could have just kept that up. Oh, it's not going to play. 1 second. The video is going to set up what's happening, and then I'm going to stop the video before you get to see what it does, because I've got the real deal, okay? So follow along. It's about a 3-minute clip, okay? Follow along with the video. Try to see if you can kind of hold on in your head everything that's going on. You're going to see electric fields and magnetic fields all over the place, okay? It's going to be a wild ride. We're going to go over it together so that we make sure we all understand exactly. What the heck? Who's the teacher in here that... Oh, no, some teacher sets it up so that it's like dark in the room and light at the board, which means he doesn't care about his students or she doesn't care about her teachers, I tell you. If you put darkness out there, people can't see their notes, they go to sleep. It means that the only thing that's important is up here, and that's totally wrong. Where's the important part of the room? It's you guys. So, you
This
specifically.
demonstration uses electromagnetic field to break a cola can into two pieces. An empty aluminum cola can is inserted into this 3-turned coil. This 400 microfarad capacitor will be charged to 3,000 volts as read by this meter, and then will be discharged through the coil. Let's charge the capacitor. When the capacitor is discharged, it creates an electron current in the coil, which increases rapidly to a large value. As the current increases, it produces a magnetic field, which also increases rapidly with time. The rapidly increasing magnetic field induces an electric field circling the axis of the coil. This electric field produces a large electron current in the aluminum can. The electrons circulating around the can in the magnetic field experience a magnetic force directed primarily radially inward, but with a smaller component directed outward along the axis of the can.
Did you catch all that? Okay, let's watch it again.
This demonstration uses an electromagnetic field to break a cola can into two
Yeah.
pieces.
Okay.
An empty
Cola
aluminum
can goes in.
is inserted into this 3-turned coil. This 400 microfarad capacitor will be charged to 1,000 volts.
We're getting
as
a lot
read
of
by this
audio
meter,
problems because
and
this
then
is
will be
now starting to
charged
produce
through the
electromagnetic
coil.
interference.
Let's charge the capacitor.
So they charge the capacitor. Takes a while.
When the capacitor is discharged, it creates an electron current in the coil, which increases rapidly to a large value.
Okay, so there's this outer coil that's inside of this wood structure, right? Okay, so the capacitor, we're going to charge the capacitor up. We're going to put a bunch of energy into this capacitor. And then capacitors are really, really good at dumping their energy really fast. Okay? So we're going to take all the energy that's stored in that capacitor, we're going to dump it into this coil. So this coil, the inside the wood, okay, is going to have a very large current flowing through it, which is going to generate what? A magnetic field, right? That magnetic field here in blue, okay, went from 0 to very big field in no time.
As the current increases, it produces a magnetic field, which also
said that.
increases rapidly with time.
I said that too.
The rapidly increasing magnetic field induces an electric field circling the axis of the coil.
Okay, where does that electric field come from? This is the changing magnet. So this is the Faraday's law electric field. And it's an eddy current, right? Or it's an eddy field, right? It's going around in a circle. So now that the changing magnetic field from the original coil has caused a circulating electric field, we have a soda can, which is made of aluminum, which has charges in it. What are those charges going to experience? A force, right? They're going to start moving around inside of the can. Well, now I have moving charges inside of a magnetic field. You are going to have a force on that can. This is called a theta pinch. Okay? Theta is an angle, and it refers to how we are going to constrain the charges. Now, if a charge experiences a force in a magnetic field, that's going to be a cross product, right? Because of the Lorentz force. Holy cow, what have we talked about so far? Capacitors, circuits, because we're charging capacitors. We've talked about making magnetic fields from currents. We've talked about making electric fields from magnetic fields. That's Faraday's law of electromagnetic induction. And now we're talking about Lorentz force law. Do you see how it's like all coming together? And if a circulating charge experiences a force, it's circulating around, that's a centripetal force towards the center. Let's see just how big that force is. The video hinted, it said it was primarily radially inward. But there is a component of the force, because we don't have a perfect thing, there is a component of the force that runs along the axis of the can. Okay? Is this an aluminum can?
Yes.
Yes. Is it full?
No.
No, there's nothing except air in the can. This is my coil. You can see my coil isn't nearly as fancy as theirs. Embedding coils in wood is kind of hard. And then I tried to 3D print something and it didn't work, and I'll explain why that didn't work in a little bit. Okay, so I'm gonna put this, I'm gonna put this like this. This is to protect the innocent. Okay. Duck. It probably won't hit you. It might bounce off of something. Lewis, you gonna catch it?
Which way will it fly?
Nah, don't. It's it's gonna be very sharp. Okay, what have I got here? I've got what is in my mind. I've told my wife what to do in the event of my death, and I've told her that if I die at work, like you get that horrible phone call from the dean, right? You know that it was this thing that caused it, okay? I do a lot of stuff in my job that it's got risk associated with it. I'm exposed to chemicals and different kinds of things. But of all the things that we have, this is by far and away the one I am most scared of, okay? And I blow stuff up for shows. I do all kinds of things. But this one is legitimately scary. This thing, if I connect myself to it, I am going from talking to you to talking to St. Peter like that. Okay? Like it is, there will be no in-between state. Okay? Assuming it's St. Peter and not the other guy. Okay, all right, yeah. The answer is, I don't know. It's big, okay? So, what I'm going to do is I'm going to charge this up to approximately 10,000 volts. We're probably going to get it up to 9,000 today, okay? So we're going to put 9,000 volts into these very big capacitors. They're kind of hard to see, but do you see those big gray things in there? Those are huge oil-filled capacitors, okay? They take a while to charge. It's going to take like a minute for them to charge up. Let me aim this again so I miss Harveen. Okay, right? Rose, we good? Okay. So I'm going to charge those up. There's a bunch of stuff in the back that's all part of the high voltage charging circuit and the triggering circuit that I'll use to fire this thing off in the first place, okay? I'll let you guys know when you can you can record now if you want, but I'm going to talk for a little bit. So definitely one hand rule on this thing, okay? But the current is unknown, it varies, but we're going to dump 9,000 volts into this coil in the span of like trillionths of a second. It's really fast. So there's a YouTube channel called the Slow Mo Guys. I really like their work because they do some really fascinating stuff with high-speed photography. And before the Slow Mo Guys, there was a different show, kind of back before the age of YouTube, and they did a similar thing where they would record with high-speed cameras and stuff. They tried to record this at about 100,000 frames per second, and they could not catch the moment when the can splits. And to my knowledge, the Slow-Mo Guys has not tried to replicate that. And frame rates nowadays can get up to like 250,000 frames per second raw, and with AI you can boost that to like 800,000 frames per second. So we still have yet to see the moment when this can get split, because it happens that fast. All right. I'm going to stop talking because I really have to concentrate on what I'm doing to keep myself safe. No other physics teachers will actually do this demonstration. Okay? They call me into their classes to do it for them because they're smart and they know it can kill them. So right now it's in a safe configuration that it can't hurt anybody, and I'm going to unsafe it so that it can cause grievous bodily harm if not treated with respect. All right. The bomb is armed. Okay. It's going to be very loud when this thing goes off. Okay, so I'm going to be wearing hearing protection because I got to have my hands free for what I'm operating down here. I will call out every 1,000 volts, okay, that we get to. And again, our goal is to get to 9,000 or 10,000, somewhere in there. It's probably going to hit 9,000 before it's going to be done. And then I'll give a countdown, 3, 2, 1, and I'll hit the button. Several things could or could not happen. One, this could go off prematurely. Sometimes it just triggers on its own, okay? In which case, it'll be exciting. And I'll need a change of underwear. Worse is if I trigger it and it doesn't go off. Because now I have a ton of energy in these capacitors and I have to diffuse it, which is exciting. Not as exciting as the can. I'd much rather diffuse it with the can, okay? So be ready for it to go off prematurely. Do cover your ears. I would recommend covering your ears. And I will call out every 1,000 and then I'll do a 3, 2, 1 for when it starts. Where's my, here we go. Always put your eye protection on before you put your hearing protection on. Okay, here we go. Oh, and this is the only thing that requires a key. All right, here we go. We are going to here we go. We're going to start charging. All right, nothing's happening. I did move this over this morning. So, well, so I think, oh, there's one part that's disconnected. All right, let's see. Well, I didn't get a chance to test it after I brought it over this morning. I was more worried about getting arrested because I was driving my car up onto the pavement. It's heavy. I didn't want to carry it. All right. 6 o'clock in the morning and the police is not good. Not a good idea. All right, let's see if we can get this to go. Nope. Oh, I left the Corsa knot. I made it safe and I made it too safe. All right. Here we go. It's charging. 1,000. That's it? That's it? Stop. Start. Come on.
Hit it a couple times.
Right? It's discharged now.
I feel like that.
You feel like what's important?
The vector is glowing.
Oh, this is just to keep it from scratching my glasses. All right, because when you fold the ends in, they rub up against the bar. Turn that off, disable the key. So which of these is not happy? Well, sometimes
It's worse when the bomb doesn't go off.
notice how many hands I'm using. Little bit of adjustment. Normally I would have gotten all the bugs out of the system already. Well, that's no good. Clean that up. Every time it fires, it causes all kinds of corrosion. Got to clean it up every once in a while. But that might have just gotten loose in the trip over. So I think I found the part that was loose.
The yellow wire.
All right, let's see if that fixed it. I hope this works. I hope it's not broken, because I'm going to have to really tear it apart. The way you stay alive is that you always have a standard operating procedure, and we're just going through it. Okay. Let's see what happens this time. I can hear you. All right, we got power, current and voltage, and dart. No, it's not working. All right, we're at 1,000. Oh, here we go. 2,000. 3,000. 4. 5. 6. 7. 8. Okay, we're going to get to 8,500 volts. You guys ready? Yep. 3, 2, 1. Did anybody get hit? No?
Like burning aluminum.
So I don't know if you can see. Okay. So So that can, so it looked like this, right? And it turned into this, right? And did you see how fast it came out? Comes out around 30 miles an hour or so, okay? 30, 40 miles an hour. But you can see the violence, right? As the electrons tried to follow that force that they were experiencing in those mixed fields, okay? So what I'm going to do is I'm going to pass these around so you can see them. Just feel that one. Is it kind of warm? A little bit. I talked too long. They're actually kind of hot after that happens. But I'm going to pass these around so you can see, right? Please be very careful. These edges are extremely sharp. Okay, knife edges on here. So please don't attack each other, and don't cut your fingers on it. Okay, so send those around so you can see that. Do it again.
Yeah! I saw the white flash. That's how insane it was.
So the white flash you saw was a big spark back here. Thank you. I always like looking ridiculous.
What if you put like your hand? Not okay. I'm actually serious question. Your hand. That's a metal, right? So like it wouldn't do anything to your bone.
Oh, if I put my hand in here? Yeah, nothing would happen. And the current would probably jump from the insulated wire into my hand. But yeah. Yeah.
Force is inward.
Yeah.
How would you right hand rule that? I'm trying to like.
The inward force.
And I can't.
So. No, come back here. Oh, no, not this one.
Well, at least Balogh will just react to
This one.
This demonstration uses an
Ah, no. You okay, Liz?
This demonstration uses an electromagnetic field to
It did turn into a projectile.
Well, I mean,
also increases rapidly with time.
it's in the middle, so it has to like.
Okay, so Rose, to
The
answer
electric
Rose's question,
field
she's like, how do you
produces a
right hand
large
rule that?
electron current in the aluminum can.
Okay, so you've got the field going along the axis of the can. You've got current coming around, so you got your velocity, you got your field, and your thumb is pointing towards the center, radially inward. It's like the cyclotron, the circulation of charges in magnetic fields that we did last chapter. And on their video,
And the electrons circulating around the can in the magnetic field experience a magnetic force directed primarily radially inward, but with a smaller component directed outward along the axis of the can.
the smaller components along the axis, that's the one that causes it to
The
fly really fast.
capacitor is now fully charged, so we can turn off the charging power supply and discharge the capacitor through the coil.
Right? Yeah,
We will
it
now
is.
repeat this action in slow motion.
They do it in slow motion, but I'm not sure that there's a reason. Okay, so let's do this again. This, by the way, is the safety wand. This is how I discharge this thing in the event that I can't discharge it any other way. There's a huge, this is like a huge resistor in here. 16,000 ohm resistor. That is very large so that it can absorb a lot of power. And it discharges it slowly and not through me. All right, I got that. I got the thing all loaded up. I took the safety out. Okay. I've got to check something. Hold on a second. Every firing, yeah. See, these are loose now. Let me tighten that one. Yeah. What I need to do is I need to rebuild it, and I need to weld the, I need to weld the wires in. Because I don't think I'm getting all the power out of the capacitors. I think some of I know a lot of it's getting lost. So. Okay, here we go. Shoot the wall?
No, I was saying like how you said there's a bunch of power loss.
Yeah.
Oh, okay.
Put the key in. All right, here we go. Charging. Almost 1,000. There's 1,000. $2,000. 3,000. 4,000. 5. 6. By the way, 3,000 is lethal. 7. 8. 8,950. Here we go. Ready? 3, 2, 1. All right, we are safe. You guys can smell it? You know what you're smelling? You're smelling burnt aluminum. You're smelling burnt plastic liner in the aluminum can. And you're smelling burnt sugar. Well, in this case, burnt aspartame.
Is it cream soda or is it?
Aspartame, because this is the 0 calorie stuff. Where did the pieces go? You found them already? Okay. Is this is the one just now?
Yeah.
So a little bit warm. Okay. So in my old office, I had a collection of these that represented me driving this setup. The very first time I got it all plugged up, I started at low voltages and I ramped it up slowly. And so I have cans that are like barely squeezed and then ones that look like really squeezed, and then finally, and like eight of them or something like that. You guys, are the ones that are being passed around, they're still going around? We'll start these in the back that way. Everybody gets to see them. Careful. Please be careful with those. All right. I didn't die! Yay! It's a good day. Always a good day that you don't die. All right, put all this away. Always put your safety gear away so you know where it is. And this is all done. And put the real safety on it. You always should be afraid of this stuff. It keeps you alive. Okay. Oh, by the way, there is one piece of this that I've never tried. The company that sent me the parts also sent me a Thompson's Flying Ring launcher, the railgun that connects to this.
That connects to that?
Yeah, I've never used it. No, it requires a little bit of a rejiggering of the system that I've never wanted to do. But in videos from the company, they show the rings. They launch them horizontally, and they go through drywall.
That's perfect. You should do it in the glass.
Listen, this building is already like kind of like, one of the TVs upstairs is already broken.
Yeah, so just keep breaking it. No, we don't keep breaking our buildings. We just don't do that. That's that.
That's the whole semester. We're done.
Goodbye. There's bits of aluminum can all over the place up here. So what's happening this Thursday? I'm done. So when you get back from spring break, right, we have the Monday. What's happening then? Thank you. So that's like a review day, right? It's lab day, but I'm just going to be here all day, and you can come in and get help. It's like GRASP, okay? What's happening Tuesday after spring break? It's also a review day. And then Thursday we're taking the exam, right? So what do you want to do this Thursday? More review?
Honestly, yeah.
I do have a video.
Nah, it's too bad.
You want to do stuff? Okay. I'll show you the video later.
Wait, what's the video?
Can we blow up more cans?
What's the video?
So we can start reviewing for the exam, right? Or helping you with your homework. Homework might be a better idea so that you have... I want you to have a little bit of spring break away from this class, right? I don't want you to lose your skills, but at the same time, when's the homework due? Next Monday is spring break? Monday after. Not during spring break. Okay. So I would love it if this chapter's homework were due, like you had it done before you started your spring break. So you could be like having fun on spring break, but also like trying to keep these ideas alive a little bit so when you come back, we can review and all that kind of stuff. That's kind of what I got in my head. So let's do homework on Thursday for this chapter, right? And then it'll be spring break, and then we'll start reviewing after you come back from spring break. See you Thursday. You're welcome.